Okay, welcome to this second day for the Photonic Integration Week. We start in a straightforward. We're having a session today which is mainly driven by industry. So we're going to have 3 companies presenting their activities related to photonic integration and microfabrication. The first speaker will be Chalony from Lightech France. She's going to talk about software tools for photonic integration. Then we will have Guido Piacenzi from RISE GmbH. And he will present some manufacturing tools for microfabrication. And finally, we will have Fernando Castaño from Austrian Microsystems talking about the photonic integration activities in their company. So let's welcome first speaker, which is Chalony from Lightech.
Thank you. Good morning, everybody. So thank you for this kind of introduction. So today I will talk about software design, indeed, and PIC design. And as I will focus my talk on a specific subject, how to create custom PDK. No, sorry. No, it's that one. Okay, now it's okay. Thanks. So here is the outline of my talk. I will start with a brief introduction, then I will talk about the way to generate a PDK, a custom PDK, using S-matrix in GDS file. I will go through some examples, and I will conclude. So, in order to simulate PIC, photonic integrated circuit, we needed some tools, of course. And so now, from the point of view of the efficiency, it's well known that models can be efficiently represent individual components of a PIC. It means we can deal with the photonic circuit, simulation level, so using a schematic description of the components. We can go up to the system of communication, so to include your PIC at the system level. And in case that you need more details on a specific component, you can come back at the passive component modeling, and I will target my talk on that part and the link from the passive component to the circuit simulation engine. How a PIC will start? So it will start from an ID. Then from the ID of the designer, it will go to a schematic level and try to organize the different components on the circuit, check a first time a behavior of the circuit. If the behavior looks like it's relevant, the idea later is to go to the mask layout, so to the layout and generate the mask to go to the foundry. But before to be able to design this circuit, we need what we call PDK, Photonic Design Kit. This PDK can be delivered by the foundry. It's quite often the case that now a designer will use PDK from a foundry. Inside Synopsys tools, RSoft, we have the possibility, so we provide some PDK library directly with our software. So it's the AAM Photonics PDK and the IMEC PDK, due to the collaboration that we have with these 2 foundries. From this PDK, you will access to all the passive and active devices from the foundry, following the design rules of the specific foundry. Same thing for HiMech, with the C-band and O-band devices available from this library. Anyway, if you are working with some other foundry, we have also from the software access to the PDA flow foundry PDK. It's a way to access to all the PDK available on the market. So here is a list of the different foundry that are available from the PDA flow service. Then, when you have this PDK model, you will design your PIC. So from the initial ID concept that you have in mind, you will test at the schematic level the physical behavior of your PIC. If the simulation, so the results looks like what you are expecting, you will go from the schematic level to the layout level. And for this part, RSoft, Synopsys RSoft tools are using Phoenix software. So we have a co-simulation with Phoenix software OptoDesigner in order to go to the mask layout. So inside Synopsys RSoft tools, we do not have access to the mask layout generation. Okay, so that's one design flow for a designer. You can use PDK from Foundry. All the Foundry are providing their own library. But time to time, it's not flexible enough. You need to augment an existing PDK library, or you need to create your own PDK, or you need, for IP purpose, you need your own component. In that case, you have to go out of this library provided by the foundries. And for that, you have to go back to the component level and do some simulation of propagation of light at the component level. In RSoft, we have some tools in order to generate the propagation of light through the component. In that case, we will use some technology from the foundry, but because don't forget, you will have to go back to the foundry to create, so with your mask, to create the PIC at the end. So we have to follow the design rules of the foundry. But then you will use a certain geometry and do a numerical simulation of propagation of light on these devices. If you can have the right behavior of this component, you will generate a S matrix and a GDS file, and that's the core of the custom PDK that you will provide at the schematic level. So now I will describe a little bit more in detail this process. Inside Synopsys RSoft, by the way, I'm working for this specific software, but you can find some similar design flow in the competition. I wanted to underline that fact. But so inside Synopsys RSoft software, we have RSoft component tools suite in order to generate the geometry of a component and then select a specific numerical method in order to propagate light through the component. From this simulation, we have a utility. We have developed a utility in order to generate the S matrix and the GDS file for this component. Here it's a ring resonator. When we have all this information as matrix, we can go up to the circuit level, and the tools that we are using in RSoft is OpSim circuit. And then when the validation is done at the photonic integrated circuit level, we can go to the mask level using Phoenix software OptoDesigner, for example. That's the design flow. The S matrix is efficient and full consistent in order to describes the behavior of a passive component, and only passive component. And also I will mention one limitation for the moment. It's just for in case, so the nonlinearity of the component is not taken into account. So that's something that we have to keep in mind in this approach of the S matrix. But when we have to propagate light through the components, it's well known that it can be time and computer consuming for a designer to do this task. It's the reason why it's so efficient and useful to use PDK provided by the foundry directly, because they are testing for their own components the full behavior of this component. It's the reason why we need to find some tricks to get to be as fast as we can in the simulation process of a component. Inside RSoft, we have different ways to proceed to be fast and accurate. First point, we have several simulation methods available inside the software. So either we can use FDTD method, BPM or eigenmode expansion, EME method. So FDTD is for finite difference time domain. BPM, it's for beam propagation method. It's not the target to explain this numerical method. They are quite well known since a long time. But so they have some advantage and disadvantage for all of them. And inside RSoft, we are giving the flexibility to the user to use one of these methods in order to be as efficient as he can for a specific component. Then, of course, it's important to use the advantage of a good computer. It's the reason why we implemented multi-threading, clustering, a non-uniform mesh at the top of this simulation numerical method. And so another good point in order to increase the speed for the designer, we are able to use pulse source. So it means at the frequency domain a broad source to generate the spectral response of the component directly in one simulation, just to avoid to do a scan over the wavelengths. Another type of advantage that we can use in order to study a component more efficiently could be what we call the effective index method, EAM method, or 2.5D simulation. And this method is, the target of this method is to map a 3D design into a 2D simulation using the effective index method. It has some advantage. It's quite accurate for a lot of design, especially for RIB waveguide and so on. And, but it's really more efficient in time of computation. We are talking about 100 times faster than a full 3D simulation. So it could also be an advantage for a designer to work with this type of methodology to design, to simulate propagation of light inside a component. And then another advantage that we are using inside RSoft is the symmetry of the component. If we can, if the component has some axis of symmetry, as a ring resonator, we can simulate and generate the S matrix on half a domain. And that's also a way to increase the speed of computation. So that's the type of approach that we developed at the component level in order to generate as fast as we can this S matrix, so the S matrix and the PDK for any type of component. Let's go through some examples. Let's start with a really simple example as a ring resonator. This ring resonator is quite well known. It's a filter, and in that case, so it's well known also that at the passive component level, we have to use FDTD in order to simulate propagation of light through this component. But FDTD can be time and computer consuming again, so it means we can simulate the full ring inside FDTD, Or we can use all the advantage of the numerical method developed inside RSoft in order to work on just half domain. We can use pulse launch field in order to generate the S matrix. And of course, we are expecting the same results from the two approach. So we did the study over the half ring using a pulse source. In one simulation, we were able to know the behavior of the port 1, so when we are launching field from this port, for each other port, output port. Same thing for the other ports, so that's all the S matrix for the different ports. And we have also the GDS file in order to go to the mask layout in the future if it's needed. From this S matrix, we are now able to create a new model, a new schematic inside the circuit, in the circuit tool. And now we can use this schematic at the circuit level to generate the behavior of the full ring. It's something that we have done in OpSim circuit. And we compare to this model to the one already built inside OpSim circuit. And we had a really good agreement between the two simulations. So we are checking, in fact, in this case, we are checking a full FDTD study of the whole ring. And the green light is from FDTD plus circuit, so schematic level analysis of a half ring. And we have a really good agreement. But of course, now it's 10 times faster using the half domain of the ring resonator plus OpSim circuit. So so we have the model for one ring, one filter. Why not to cascade all this ring and to add this ring inside a larger design using also PDK from library? And it's what we have developed here with some ring resonator generated from the passive component tools, and some PDK. Here it's some cross-section, waveguide from a PDK library. And we can combine all together and check what type of behavior we will have on this design by mixing existing PDK and our custom PDK. I wanted also to underline one aspect to give more flexibility for the designer. When you are designing at the schematic level your peak, time to times, you don't know exactly the right position of the different components that you will have on your mask. And you don't know exactly the rules that the mask layout generator will follow for your component. For that, we have developed what we called elastic connector. This connector will receive some information from the mask layout software in order to adapt its length related to the position on the mask. So you will use this elastic connector at the schematic level. Then you will translate the schematic into the mask. OptoDesigner will define, following the design rules of the foundry, the layout of this connector and the shape that he will have. And he will go back, he will give back the information to OpSim circuit, to the schematic physical level analysis, and we can study the behavior of this peak, including the right length of the connector. That's also a flexibility that we are giving inside the tools to the designer. Okay, but let's come back on another example of custom PDK. In that case, we are designing our own couplers. And this type of couplers so we are able to adjust the distance here. Is that the blue part of the segment inside the couplers to change the wavelengths filtered by the coupler, and so it's pretty small. It's 2.5 band radius. And so the idea is to cascade all these couplers to create a filters, and the full filters will be less than 100 micrometers. So it's from a paper, and the idea is to create a filters with this type of geometry. Inside the component tools, at the component level, we can study again the transfer matrix for the coupler, for the different ports, and generate the S matrix of the coupler for different type of distance. For this type of design, FDTD, so full wave in RSoft, will be the right software to use. Again, we can use advantage of 2.5D or clustering in order to be fast for the design of this component and the study of this component. And we will generate the full PDK information, S matrix plus mask, GDS file, sorry, for different type of coupler with different lengths D. We can then use these PDKs, our custom PDK, at the circuit level to cascade them and to create the filter. So the filter will looks like this, and at the point of view of the mask layout, it would be something like that. Then we can test the filter at the circuit level and check the FSR. It's something like more than 80 nanometers for the FSR. And we can also study the behavior of this filter for different distance of that we included in the couplers. And now, by scanning over the distance, we are scanning also the selected wavelengths of the filter. Okay, so we have one line of the filter, and now we can go for something more complex with a 4-channel filtering using our custom PDK. So we cascade several, so 8 couplers for different distance. Each of them are filtering a specific wavelength, and we create a source, and this source was, so all the splitters, waveguide, was generated from existing PDK from Foundry. And it doesn't matter the foundries that we are using at that stage, by the way. So we have our source, the filter, and we place also the sensor part, so the photo detection. And again, we are using a component from Foundry. And now we can test at the schematic level the behavior of the filter. So first, we can generate the mask of this filter, again using a Phoenix Software OptoDesigner co-simulation. And then we can test each arm of these filters and check the height diagram for the 4 arms of the filter. And it's a pretty good height diagram. It's quite open for each channel. So it's a way to validate the behavior of the filter, and then we can decide or not to go to the mask generation, to go to the Foundry with this mask. Okay, so let's go for the conclusion of my talk. So I wanted to show you that there is different way to deal with the peak design. Of course, so now it's well known that each foundry are providing its own PDK. It's quite efficient to use this PDK to start your own peak. But keep in mind that time to time it's good to have flexibility if you need to generate your own IP, for example. And in that case, you will need to access to another design flow process, and one of them could be Synopsys RSoft tools, and in that way you will generate your own custom PDK from component and go then to the schematic layer, level in order to study the full peak inside RSoft, and following the foundry technology rules that you have available from the foundry. Thank you for your attention.
Okay, thank you, Marion, for your talk. Now it's time for questions.
Yeah, thank you very much for your presentation. I just wanted to make a quick question. So you mentioned that you are already having the PDK implemented for AIM Photonics and for IMEC foundries.
Yes.
Which are both of them silicon photonics foundries.
Yes.
Are you planning to extend this to other silicon photonics foundries or to other material platforms like indium phosphide or silicon nitride?
So yeah, on the Synopsys side, there is no target to be focused on one technology. For the moment, the collaboration was done with IMEC and AAM. But so first, from the PDA flow, we have access to the other foundry as other software from the PDA flow. So it means if you are dealing with indium phosphide, you can access to this technology from PDA flow. And then inside RSoft, so at the schematic level, it's fully agnostic. We really don't care about the materials. So that's not a limitation of the engine. And of course, we are open for more collaboration and to implement more and more PDK inside the software. But I know that you're also dealing with Foundry. All of them are not so pleased to share all the information. We know that. They are still quite, let's say so. They are taking care of the kind of information that they are sharing. It's not so easy to start a good collaboration with them.
Yeah, it's strange because from my opinion, it would be great for foundries to actually have more softwares implementing their PDK so more users can actually access that. But
I agree with you.
It's strange.
Fully agree with you.
Okay, thank you.
Any other question? No more questions, then we move to next speaker. Thanks, speaker again.